So as I advertised on the email in Moodle, we'll work through the 2013 Semester 1 final exam. It's a 3-hour exam and we have 50 minutes, so you'll obviously be able to go a lot more slowly than I will in the lecture today. And we're only going to do questions 1, 2, 5 and 6. That's the material that we've covered in the past 4 weeks. Okay? And they're 4 of the 6 questions. The other 2 are on op-amps and digital, but I'll focus on what we've done the last 4 weeks as revision for that period. You don't take anything with you. So if you want to pull that exam up, it should be on the Moodle site in the exam section, this exam. No calculators, no open books, no anything, no toilet paper, no lunch, no whatever you're not allowed in the exam. Most relevant for you, no calculators. There's the latest entry. Quite a lot of things to notice. There's a lot of detail here. We've got the staff with the capacitor on the end. I can see LEDs, chips there in the hand, lots of gates. Down here, there's a little bit of a blow up. That's me. Very good, dressed up as a 1970s tennis player. And I can see here, it looks to me like Tyrion Lannister from Game of Thrones. And that looks mighty like Daniel Wells from the North Melbourne football team. This is pretty darn good, is what I'm saying. 30 likes at the moment, so if you like it, if you want it to win the People's Choice Award, get on there and vote now. I think quite an impressive effort. So the last several years, question 1's on nodal and mesh analysis for 10 marks. The same again, it will be for your exam. So first question, a nodal analysis to find a current I. So we have to remember, we say where are all the nodes? Let's call one of them ground. Well, let's say it's this one, not specified. Let's say that's node 1, voltage 1, and this is node 2, voltage 2. Nodal analysis, we're meant to find V1 and V2, and then find whatever, we have to find then I in this case. But let's find V1 and V2. We first say, are there any voltage sources anywhere there? No, there aren't. So it's the stock standard Kirchhoff's current law at each node in terms of the node voltages. So at the first one we go to maybe is node 1. That current is V1 on 1 ohm, 1 ohm. That current is V1 minus V2 on 1. I like the way the resistors have been chosen. You haven't got calculators, so numbers look, they start to be reasonable. And I have to add that current, which is minus 5 equals 0. Or in other words, 2V1 minus V2 equals 5. There's our first equation. I then go to the other node, node 2, and I'll say this one here is V2 minus V2 minus V1 on 1. That one there down through the 1 ohm resistor will be V2 on 1 ohm. And that one there is plus 1 equals 0. So if I simplify that, I get minus V1 plus 2V2 equals minus 1. That's sort of, in some ways, the important circuitsy bit. You've got the two equations. You'd certainly get some marks, at least 2 out of 4, for getting the two equations correct. You have to solve them. You don't have a calculator, but I hope you could solve those two. To save a little bit of time, I won't solve them live. I'll just tell you that, well, you know, you can add this equation 1 plus 2 times equation 2, whatever you want to do it, eliminate one of the variables and solve, and you'll see that the solution is V1 equals 3 volts, V2 equals 1 volt. So first write equations, second find V1 and V2, and don't forget the question asks us to find the current I, which is up here, flowing through that 1 ohm resistor. What is the current I? Shut up! Thank you. I heard someone say it, V1 minus V2 on 1 ohm, which will be equal to 2 amps. Okay? So I is 2 amps. There's your 4 marks. Cool, you've locked that one away. You can start feeling good. Any questions about it? Stock standard 2-node nodal analysis. Hopefully you can at least write down the two equations. Hopefully you can solve them. Two linear simultaneous equations. And then don't forget, go back and read the question and ask, did you just have to find the node voltages or did you have to find something else? There's one from last year. Right, 1.2 is mesh analysis. See if you can do it in melts. I think there's... I'm very pleased to see that Daniel Wells is second on the leaderboard with 49, and I think one person's on 50 in front. And there's a 48. All of these people could win. 4 questions today. So I want you to stay sharp. So do some work, attempt the question, get more out of the lecture. So there's one equation for the left mesh. There's your second equation from the right mesh. 1 plus 2 times the first equation plus 2 times the second equation will eliminate I1. You can solve for I2. So 10. Whoa. Whoa. Mob. 10. I was going to count backwards from 10. Good. All right, 10, 9, 8, 7. We've got to move. 6, 5, 4, 3, 2. I've got to solve those two equations. I get what? I1 equals minus 0.5 amps. I2 equals 1 amp. The numbers... Okay, no calculator, but the numbers are generally pretty nice to deal with, so that will remain. So the two equations, we solve them. We go back and run... Quiet, please. We go back and remember that actually the question asked us to find this current I, but I is equal to I1 minus I2, which is minus 1.5 amps. And about 65 out of 90 responses did in fact answer minus 1.5 amps. So that's fantastic. Well done. That was from last semester. One of the MELTS questions was, what is the resistance of bacon? So we're there actually measuring the resistance of bacon in lectures with a multimeter and a very brave student. The bacon was about 6 weeks old because, and it didn't smell very good, but never mind. So now we have, that's fine, but they're kind of the simple cases. Whatever you put in melts, I will do. I am your servant. Whatever we put in... No. Those two were kind of standard, so we've got to have one that has voltage sources and dependent sources in it. And in this case, it's a bigger one, but you actually only need to write down the equations, you don't need to solve them. Okay, so yeah, solve 2 by 2s, that's fine. For the bigger one, I'm just interested here in whether you can write down the equations, not if you can solve them. So that would be a typical philosophy in writing questions as well. So here we identify the ground, well it's already done for us, plus 3 nodes, V1, V2 and V3, the 3 nodes and they're labelled. So we first, well, yell out an equation. Don't speak, how rude. No, exactly. V1 minus V2 equals 10. There's equation 1. V1 minus V2 equals 10. Everywhere there's a voltage source we go and we immediately write down an equation. Either a node voltage equals something, or in this case, because it's between nodes 1 and 2, the difference in voltages. There is equation 1. Well, there aren't any other voltage sources, and I need 2 more equations, so I'm going to have to do 2 Kirchhoff current law applications. If I start with this one, V at node 3, I would get V3 minus V2 on 1 plus V3 on 1 plus 1 equals 0. If you were lazy, you could probably just leave it at that. That is an equation. Perhaps you'd want to simplify it to something else. But that's the heart of it. That's there, we're done. That's fine. It's all in terms of V2 and V3. So that's the second equation. What's the third? Where's the third one going to come from? Supernode. Exactly right. Here it is. I include those 2 nodes now. I can't really do KCL at either one of them because of the voltage source. I don't know what the current is there. I don't want to introduce an unknown current variable I. So I just do Kirchhoff's current law at that supernode. I will then say that current there is minus 4 IX. That current there is V1 on 1, so plus V1 on 1. And I have to now add this one, which is V2 on 1, and that one, which is V2 minus V3 on 1. So the sum of all of those things equals 0. Do I stop there? No, there's a pesky IX over here because it was a dependent current source. I don't want IX, I've got to get rid of it. But what is IX? IX is this thing here, which must be V2 on 1. So I substitute that in for IX, and I've got my third equation. Only after I've substituted it in. It says 3 equations, so I couldn't leave it like that and then write IX equals V2 on 1. I'd have to substitute it in for IX. Otherwise, it's like 4 equations in 4 unknowns. So a minor point, but I should actually replace that by V2 on 1. Replace IX by its value in terms of the node voltages. So that's the other thing. All equations in terms of V1, V2 and V3. And you just stop there. It's actually quicker. You don't have to solve the equations. And it was worth 3 marks. Good. Any questions? That's pretty much all you have to do for node voltage and node analysis, node voltage analysis or mesh current analysis. That's minimalist. Minimalist. It's in the lead at the moment. So if you want Moses to beat it, you better vote for Moses. So these marks, by the way, they add up to 70. So this is, again, roughly speaking, a sixth, a little bit less than a sixth of the exam paper. Should take about 20 minutes if you're doing it yourselves. Superposition and Thevenin and Norton. So week 9. Quiet, please. Quiet. Use superposition to find the voltage across the 4 ohm resistor in the circuit shown above. So you have to know what superposition is. The idea of looking at one source at a time, one independent source at a time, and adding up the results. So let's first say get rid of the current source. How do I get rid of a current source? Open circuit. If I open circuit here, all this is gone. It's an open circuit, no current flowing. I can ignore it. And I'm going to find what I'm going to call V1 because it's not the final answer. It's just the result due to the voltage source alone. What I'm left with is a single loop, a total resistance of 2 plus 2 plus 4, which is 8. So a current of 1 amp will flow. So what is V1? 4 volts. I could have done a voltage divider. I just work out the current I, and multiply it by 4, however you want to do it. But V1 will equal 8 volts by 4 ohms on 2 ohms plus 2 ohms plus 4 ohms, which is 4 volts. Half the voltage is going to drop across the 4 ohm resistor. But if you think, oh, I've forgotten voltage divider, we'll just work out the current using Ohm's law, and you're done. So if just the voltage source is there, I know V1, that would be 4 volts. Now I get rid of the voltage source by making it a what? Short circuit. That's gone there, that's irrelevant, that's a short circuit. I have this 4 amps flowing here, and it can split between 2 paths, classic current divider. So let's work out this current here that flows there, I, and then I'll multiply it by 4 to get the voltage. And I'll call this V2 now, because it's just the one just due to the current source acting alone. So I will be the 4 amps, and it can split either down this path with just 2 ohms or this path with 6. So how much goes through the 6? Well, I do the other resistance, 2 divided by 2 plus 6, which is 1 amp. So 1 amp flows through the 6 ohms, 3 amps flows through the 2 ohms, such that the voltage drop across both is the same at 6 volts. So if I is 1 amp, V2 will be 4 ohms times 1 amp, which is 4 volts. So both circuits, when you only have one source acting, ended up being one of the sort of simpler ones to analyse. A single loop or a single node pair circuit, nice and easy to analyse. I haven't finished. What's V? V1 plus V2. So finally, by superposition, V equals V1 plus V2 equals 8 volts. Any questions? Yep.
Does the 1 ohm resistor affect the solution current?
Does the... No, because there's just because that's a current source of 4 amps, there is 4 amps flowing here like this, and it just still splits between those other two. So that 1 ohm could have been a 10 ohm, could have been a 100 ohm, could have been a 1,000 ohm resistance. It would not have changed the voltage that I got in that case. And in fact didn't change it in the other case either. So it doesn't matter what that resistor is, it doesn't enter into the solution. There was one. Now it says, oh look, find the Thevenin equivalent. Now, can I suggest, is there anything similar about that circuit to the one you just analysed? Oh, it's the same. Okay, good. You just found V for that circuit. Well, what is V? V Thevenin. It is the open circuit voltage. You've already found the Thevenin. Now, a lot of people would just redo it from the start and try and not realising that, oh, hang on, maybe these are all parts of the same sort of question. Maybe they're related. So V open circuit equals V is 8 volts. We've already found it. So the Thevenin voltage is 8 volts. We only need to find the Thevenin resistance, the equivalent resistance at terminals AB. That is the next melts question. So bear with me while I pose that for you. Okay, that is up, that question. Thirty seconds. Ten seconds. Doesn't look good. Okay. There are no dependent sources, so look, an easy way to do it is get rid of all the sources and find the equivalent resistance. I open circuit that, so it's gone again, and I short circuit that. I look in here and say, what's the equivalent resistance? What is it? How could it be 4? It's 4 in parallel with 2 plus 2. It would only be 4 if I open circuited the voltage source as well. This point here and this point here, I could go that way or that way. It's the same voltage across the 2 plus 2 as there is across the 4. So it's 2 ohms. And that would be the Thevenin equivalent circuit. Now, over half of the respondents put 4. So I don't know if someone wants to say why, or if you're still confused. Is anyone who put? Yep.
I just thought when you were put there, you that resistor on the 4 on there.
But if I just maybe I'll repeat the question. We did in lecture 6. What's the equivalent resistance? Looking into some big series parallel combination, and you all did it. This in parallel with this plus this, and then it's in parallel with that, and reduced it right down. It's the same way to look at that question. Redraw the circuit, maybe, just to make it a bit clearer. I try to redraw it by scratching things out, but it might be a little clearer to just replace the voltage with a short circuit, get rid of the other part with an open circuit. But is it okay now? You can see. Okay, good.
Do we have to consider the 4 ohm resistor or not? Because isn't that we are going to find the open circuit voltage at that point?
No, so don't be confused. I said at the terminals AB, what is the Thevenin resistance? That 4 ohm resistor is there. It's not a load resistor. If it was out here, then it's to the right of the terminals AB, and you don't include it. Yep.
Yeah, what about with the current going to the 4 ohm resistor?
Sorry?
Current going to the 4 ohm resistor, like in superposition. So to work out the equivalent resistance, you get that the current. You already know the voltage, you got the current, so you work out the current. Yeah, does that make sense?
So look, another way to do it would have been to leave everything in and find the short circuit current. You could do it that way as well. But you've got another circuit to analyse, and I think it would take more time.
Yeah, but I think it's something like in the question before.
Sorry, excuse me? Can't hear the question.
In the question before, you remember we were trying to work out I, right? Can we go back there?
Which question?
Like, yeah, start.
Yep.
You said I equals 4 amps times 2 divided by 6, right? Isn't that the current going down, going the other way? Not I, but the other one?
So firstly, if I short circuit the terminals, I've got a totally new circuit to analyse.
Yeah, I understand, but but for this question, in particular,
Tell you what, can you ask me afterwards? Because I think we should move on. So just to finish, you could have shorted it, found when you've done it, that would disappear, it would become irrelevant, and you could have analysed that circuit and found the current.
So the 4 is not a load.
The 4 is not a load. Did I say it was a load? No. And this causes some confusion because of this notion of, when we did some examples, it talked about this load resistance. Nothing says load resistance there. It says find the Thevenin equivalent of this circuit to the left of the terminal. You never are going to take out a resistor. Okay? And maybe that was causing the confusion, because if you took the resistor out, you would have got 4 ohms as well. I didn't get that. But apparently it was very cutting edge. It was so cutting edge that no one else in the class got it. But it was so right at the edge, apparently. So maybe some of you. Doesn't mean anything to me. All right. This 4 marks can be done in 10 seconds. If you know what you are doing, there are no calculations to do. The answer is immediate. But it's slightly different. So it sort of is, I think, a nice separator. If I've given any box like that, and I want to find a Thevenin equivalent and Norton equivalent, I need to find the open circuit voltage and the short circuit current. Here I'm not given the circuit, but I'm given the VI relationship. What is the open circuit voltage? 8. it was the voltage corresponding to no current flow. So that must be this value here, which is 8. What is the short circuit current? No voltage. Short circuit, 0 volts. Across there, 2 amps. What is R Thevenin? VOC divided by ISC, which is 4 ohms. I've finished. That was 4 marks in 10 seconds. I suppose you should do this to finish off and say this is the Thevenin, 8 volts, 4 ohms, and this is the Norton, and it checks that you put them in series, the resistor in series for Thevenin and in parallel for Norton. 2 amps, 4 ohms, and then say this is Thevenin and that is Norton. Okay. Quite possibly the same question is in this year's exam. I can't remember, but it might be. Or it was in semester 2's last year as well. Anyway. Yes, question? Sorry? Do you need to know? Yeah, you should. I think you should draw the circuits. If you just said VOC, ISC and RThev, that's not enough. There is a little bit more in showing the topology of the 2 circuits, showing that you put the resistor in parallel with the current source for Norton and so on. So I would definitely draw the circuits. So we've seen that one before. It's actually 46 likes in second place. We'll see how it goes. Let's jump to 5. So question 3 was op amps, question 4 was digital, and now we go to a 15-mark question on capacitors, inductors and transient analysis. The first one may just test the basic I equals C times the V by dt, the relationships in the time domain between current and voltage for a capacitor or an inductor. And that's what this one does. You're given the current waveform and told you're going through a 10 microfarad capacitor. And you want to find the voltage. Given the current, find the voltage. Well, I'd hope you wouldn't need it, but if you wanted to, this was in the formula sheet. But you should know, I is the derivative of the voltage, or voltage is the integral of the current, essentially. But if you panicked and lost your mind, look to the formula sheet. You never know what you'll find there. So we need to know, we're given this I of t, because that's this thing here, the current through the capacitor, and we just need to find the voltage. We're told the initial one because it says the capacitor is initially uncharged. So we can get rid of that. That's 0. And we're told C is 10 microfarads, which is 10 times 10 to the minus 6 farads. So you just need to know what micro means. So we've got C is 10 to the minus 5 farads, and we're given I. So plugging it in there, VCT must be 10 to the 5 times the integral from 0 to t of the current, which is a constant at 1 milliamp. So 10 to the minus 3 amps. Detour. When's that true up until? That's only true up until only when the current is at 10 to the minus 3, which is only up until this point here, 2 milliseconds. So that's for t between 0 and 2 milliseconds. And after that it just stops. Whatever value it got to, the current drops to 0 so the voltage will just stay at that value. If you integrate that, hopefully you know you're going to go up in a straight line and then just be flat. So the only issue you've got is what value does it get up to at 2? So if we, hopefully you can integrate a constant. I actually forgot how to, but that's me. So it's the constant out the front times t. So it increases linearly between 0 and 2 milliseconds. And in particular, what is the value of voltage that it gets up to at 2 milliseconds? If I plug in 2 by 10 to the minus 3 there, what do I get? What's VC at 2 milliseconds? What's 100 times 2 on 1,000? 0.2. So it'll get up to 0.2 volts at 2 milliseconds and then stay flat. So the thing was to draw it on that. This t in milliseconds is already labelled. So let's just say, well, we're going to go up like that to there and then go flat, and I just have to label that at 0.2. So that would be 0.1. So that's it. Starts at 0, increases linearly, and then stops when the current was 0. There's no change to the voltage. Doesn't drop to 0, it just stays at the value. All right, the third Meltz question, I suspect the last one we will get to today. Now it's going to be a first order question. Something happens at t equals 0, and so you first analyse it before the switch is changed. The switch position is changed. So you do a DC steady state analysis of the circuit where the capacitor can be treated as an open circuit, and I want to find the initial voltage. So it's as if the capacitor's not there, and I want to find the voltage on that 6 k ohm resistor up the top. The Meltz question is open. Just maybe to help a little bit, that 6 voltage source tells me that this voltage here is 6 volts, of course. And what I'm after is this voltage here, across, well, this one here. And the capacitor is an open circuit. Give you 30 seconds. All right, blocking it now. So 70, 60 out of 80 basically said 3 volts, and indeed that's the case. There's 6 volts across the series combination of the 6K and the 6K resistor, so half of that 6 volts is going to drop across both of those resistors. So 3 volts across each. Otherwise here you can work out the current. It must be 6 volts on 12 k ohms, which is half a milliamp, so that VC0 will be 6 times a half, which is 3. So 3 volts are sitting there across the capacitor. And then I open this switch here. Well, first, what is the value of VCT as soon as I've opened the switch now? This is now opened and this is gone. What is it? 3 volts, the same as it was before. It can't jump. Remember, capacitors are like white man, as are inductors. Voltage on the capacitor can't jump. VC0 plus is VC0 minus. It's 3 volts. We just worked it out. That only takes 1 second to get that one mark. 1 second. So VC0 is 3 volts. It's continuous. 0 plus is 0 minus is 0. 3 volts. So I've got my new circuit. Bit of quiet, please. I can appreciate it's 3:55. What do you want me to do? Do you want me to finish question 5? Stop here.
Keep going.
Okay. If you've got something at 4, what? If you've got something at 4 o'clock, I understand if you need to leave. That's gone. We'll be a bit faster if you're quiet. What does the circuit, this says find a differential equation for VCT. Now there's a single capacitor there. Tell me about those 3 resistance. What's the equivalent resistance seen by the capacitor? 6 in parallel with 12. Exactly, thank you. 6 in parallel with 12 is the resistance seen by that capacitor. Can we see that at these terminals here? There's this in parallel with that. 6 in parallel with 12. So the circuit, I'm going to replace it with, this is like doing this Thevenin equivalent trick, but there's no voltage source there. I can replace it by a single resistance of value 4 k ohms. And there's my 100 microfarad capacitor. And I want to know an equation for this voltage VCT. So it doesn't say, oh, just tell me what VCT is. It actually wants you to give the differential equation satisfied by VCT. Well, you might remember how we did it. We just said, well, what's the current there? What's the current there? They must sum to 0. So if I call that IC, I call that IR. We know that IC plus IR equals 0. But what is IC? Well, it's C times the VC dt. IV equation for a capacitor. What is the current IR through that 4 k ohm resistor? In terms of VC, VC divided by R. VC is also the voltage on the resistor, so the current through the resistor will be VC on R. That equals 0, Kirchhoff's current law. IC plus IR equals 0. We can simplify it if you like. The VC dt plus 1 on RC, VC equals 0, where R is 4 k ohms and C is 100 microfarads. So that's it. That's like how we very started our first analysis of RC circuits. If you had to find your differential equation, hang on. Is there a question with that? You just need to really know that I equals C times dV by dt. That's what introduces the differential equation. Okay? I don't need long. A couple of minutes to finish question 5. Now I want to find what VCT is. I start at 3 volts. What do I finish up at infinity? 0. How fast do I get there? It's controlled by the time constant, which is the equivalent resistance times C. It's over here. It's R times C, where R's 4 k ohms and C's 100 microfarads. So C is 4 k ohms times 100 microfarads, the equivalent resistance times the capacitors, which is 0.4 seconds. That's everything I need to know. Starts at 3, ends up at 0, and how fast does it get there? It's controlled by the time constant. So we remember, hopefully, that VCT is the final value plus the initial minus the final, e to the minus t on tau. We've got all of those things. This is 3 e to the minus t on 0.4 volts. 3 to 0 with a time constant of 0.4 seconds. I don't like having to draw because I'm not very good, but the person who wrote this question does like to draw. So I said